Now let us look at the second numerical asked in VT basically examination. The vapor compression refrigerator of 10 ton capacity from Freon 12 has a refrigerant has an evaporator temperature of minus 10 degrees centigrade and a condensate temperature of 30 degrees centigrade. Assuming simple saturation cycle, determine mass flow rate of the refrigerant in kg per minute. Power input COP, take CPV, CP of the vapor at 0.72 kilojoules per kg. See, they are given a simple saturation cycle. So what it is understood that the vapor is dry and saturated at the end of compression. Okay, this is a special case. Please understand. We will be looking at two of the special case. One is at the end of the compression it is uh, saturated. So the graph TS graph as well as pH graphs will become like this. A and D. B is the compression end of compression. It is lying on the saturation line. So this value you can get, and this C value is also lying on saturated liquid line. So this value you will get directly from the tables. Similarly, in pH diagram, enthalpy diagram, C enthalpy at C saturated liquid and enthalpy at B directly you will get from the uh, table itself for Freon. Now the refrigeration capacity is 10 tons. That is multiplied by 3.5 is 35 kilowatt. Okay. The thermodynamic properties of Freon to all refrigerant, which is used in the old fridges and all. This they are given for minus 10 degrees. They are taken these values and plus 30 degrees. Now minus 10 degrees. See, please understand. This is the HF enthalpy of the fluid. This is the enthalpy of fluid in the wet region. And this is the enthalpy of the gas, saturated vapor on the saturated vapor line. This enthalpy is on the saturated liquid line. Similarly, these are the entropies on saturated liquid line, and these are the entropy on saturated vapor line. Okay. Now mass flow rate is equal to refrigeration capacity divided by refrigeration effect. So refrigeration capacity is equal to mass flow rate into refrigeration effect, that is HA minus HD. 2100 that is given. He has taken in minutes because he asked for mass flow rate in minutes. Now pH diagram, HD is equal to HC, constant entropy it is. Therefore 2100 is equal to m dash dot H into HA minus HC. So please listen, as a liquid, the refrigerant will be in the liquid state after condensation. Hence the enthalpy of the saturated liquid at point C, this point, is taken. Okay, that is 64.5 kilojoules. Now, but what is HA? Now to find out HA, we have to find out HF is equal to X into HFG. X is the dryness fraction. Okay. Now you are substituting these values of HF and HFG in this equation. So you can find out the dryness fraction X. Okay. Now in the TS diagram for the entropy, here you see entropy at B is equal to entropy at A. Entropy at B is directly the saturated gas, but entropy at A is equal to entropy of the fluid plus entropy of the mixture into the dryness fraction. This is like from when you are studying steam, these are the formulas used. From this table we can use out, we find out X is equal to 0.97 dry. Now the equation, you will substitute this X value in HA equation. So HA is equal to 178 kilojoules. Okay. So the equation at mass flow rate you can find out 18.48 kilojoules. Now work input to the compressor is equal to mass flow rate divided by 60 into HB minus HA. Enthalpy at B minus enthalpy at A. So from the table, enthalpy at B is directly available from the table. Dry vapor is dry at the end of compression. So the power is 6.54 kilowatt. So here please understand, this kilowatt means it has, we have calculated for per minute, so that is why it is divided by 60. Okay. And to find COP, COP is called a refrigeration effect divided by work done, that is A minus enthalpy at A minus enthalpy at C divided by enthalpy of B minus enthalpy at A. This substituting the value, we get COP value as 5.3. Two things you have to understand here, because we are calculated refrigerant flow per minute, that is here divided by 60, and the values of HB, because vapor is dry and under the compression, this HB value taken